Yes.
Yes.
Great.
Okay.
Okay. Yeah, it's my pleasure to also introduce Professor Alain Pumir, who will be talking about settling and collision of ice crystals in turbulent clouds. So over to you, Alain.
Thank you. Okay, so I guess to begin with, I would like to sort of say that, of course, I've seen how much effort the poor organizers have put to sort of make these things happen. They went through hell because of unfortunate circumstances that we know. Well, it would have been so much better to be all together, and that would have facilitated discussions. Nonetheless, well, Zoom has its shortcomings, but it has the merits that it's there and that we can still use it and communicate. And we all hope, of course, that things will get better and hopefully it won't get much worse. Worse not being, well, we probably cannot quite exclude the worst, but at least we just can be hopeful. Okay, so I'll be talking about turbulent clouds and ice crystals. So I guess many of the, well, some of the ideas that I will be discussing have been already introduced in previous talks. So nonetheless, the context is a bit different, and the story, I hope, has its own interest, in part because of other issues that are important to all of us. So people who have been contributing, there's my student, Zubair Sheikh, who was postdoc, PhD with me, and who is now back home to his home, well, on your part of the world, of the part of the our Indian colleagues of the world, namely in Lahore, Pakistan. Then my two colleagues in Lyon, Ornazo and Levesque, and things would not have been possible without the extraordinary help from Bernard and Kristian. So that's being understood that anything stupid I could say is mine and not theirs. Okay, well, let's see. How do I, yeah, okay, fine. So what is the story about? So, well, we all know that, well, cloud, okay, fine, so there are zillions of them, we've all seen that. But we also know that as we go up in altitude, temperature goes down. So there, and well, it goes down and can go below 0, indicated as here, or below -40, indicating as here. So of course, if the cloud stays below the line at which temperature is 0, well, then there is water, which is the thing that is of interest, is always in the liquid phase, which is a stable phase. The liquid phase becomes metastable above 0 and becomes completely unstable above -40. So in between these two lines where you get 0 and -40, well, give or take, you have both phases present, and way above you have ice. Okay, so that's of course the cast, and well, then you know, so lots of us have been discussing water droplets, which are living here, but some other things are possible. Okay, so when I guess what if you look at the literature in terms of ice crystal, well, there are zillions of ice crystals. So the one I will be focusing on are these sort of platelets, which are shaped like so. These sort of very, very skinny little things, typically with these hexagonal shapes. And they are dominant in some sense in the range of temperature. So if you go much, much higher, that's a different story. But at least in some range of a parameter, you have this. So then if you have these little platelets, well, of course, they can move about. And because they are very heavy compared to air, the difference between the aspect ratio of the density of the ice and of the air is roughly a factor of 1,000. So if all these things just settle, that's unavoidable. But they can also orient in some particular way. And so, in fact, this orientation issue has been, well, can be sort of beautifully illustrated by what's called light pillars. So that's what's happening, for example, when you have, well, you know, in some cold environment, when the air is very, very still. I mean, there's no motion, no turbulence, no nothing. And then, so what may happen, so that's on the left, you see what's happening, and on the right, you see the explanation. So effectively, because these little crystals get aligned parallel to, like so, like illustrated here, you have this reflection phenomenon on this effect of which generate these light pillars. That's something that, in fact, has been noticed many times ago. Well, in the scientific literature, I think that's one of the earliest paper. And that is actually something very useful because you can use this idea to sort of actually study the orientation of these beasts. But I was telling you that that's happening when the air is still. Well, of course, my story is about turbulence. So the things that's not always at rest. On the contrary, there is plenty of action. And then turbulence, of course, tends to randomize the orientation of my anisotropic particles. And I guess the question, one of the questions that we are asking is what is the result of this interaction between this stabilizing, well, obviously these things which tend to sort of become aligned in a particular manner when there is no motion, and the effect of turbulence when it happens high up. Okay, so now, of course, it's some sort of an idiotic theoretical question. Well, not completely. Because what's happening in some clouds, if you have this sort of a little these aligned particles, well, then what they can do for you is that they can reflect light coming from the sun, for example. So, and instead of having the light from the sun going all the way down to the earth, that can bounce up some light, reflect some light, and effectively cool, well, reduce the amount of heat absorbed by the earth. On the other hand, the same effect also acts because the reflection of the infrared radiation from the earth, and that's a cooling effect, is also reduced by that. As a result, it's sort of known, well, it's, if you look at the literature, people say that these clouds, some of these clouds were, it's suspected that these ice crystals are very oriented. Actually, they generally contribute to the greenhouse effect. So in other words, there's more, it sort of prevents more reduction of the temperature that increases the temperature than reduction of the temperature. But anyway, so that's something that given was a question being asked about climate, etc., that's something that may be interesting on its own. In fact, well, sure, having said that, some people are worried about that. And there has been a bunch of satellites which have been circling, orbiting around the Earth and measuring the orientation of these little crystals from above, using effectively this principle of shining some light and seeing the sort of reflected signal and analyzing it. That sort of gives you an idea of how much alignment there is. So so here's this sort of two graphs look pretty much the same. So the horizontally there is this velocity of wind, think of it as turbulence, and so you see basically that there is some alignment which sort of goes down when turbulence increases. But there's a little catch. So here there's a very cold clouds and sort of warmer clouds. And the difference comes if you look at what's in the vertical axis. So in fact, here there is far more alignment than here, which I guess is pretty consistent with the fact that the crystals that can reflect the ice are the ones that occur in this cloud, which are warmer than -30. I told you that my little platelets that are very efficient at reflecting are in the -20, -10 range. So that's effectively what's happening. Well, what these measurements, satellite measurement campaigns have given you. So there is some alignment. It's important. Now, if you sort of ask yourself questions and sort of try to ask people who know, you realize that not everything is so clear. But at least that much of what I'm showing here is clear. Okay, so that's part of the story. The other part of the story, which, so in a sense, that was about this settling aspect in my title. The other part, which I will be showing, has to do with aggregation or collisions. So that's a picture of a cumulonimbus clouds. So that's my 0 degrees Celsius line. Effectively, what people know is that effectively most of the nucleation of the generation from aerosols to droplets is happening at a relatively high temperature, I mean above 0. Then what seems to be happening is that the thing is being convected up by some big updrafts, and that sort of effectively generates some little crystals which may aggregate between themselves and between crystals, or also aggregate with some water, which would be in metastable state. So the process I'm looking at now is this one. So this aggregation process, which I think of sort of taking some crystals and asking myself what will bring them together and forming some bigger aggregates. So to sort of give you some other vision of it, so that's again my familiar little crystal that I was showing you. So the scale here is 100 microns, 0.1 millimeter. And so that after that has collided and aggregated, that sort of gives you this monster of the order of a millimeter. And that's something, a good candidate to sort of do things like whirlpools or snow, depending on the context. So I guess the question, what we're doing, we want to ask is what is it? What makes the things? Well, what is the rate at which the things will accumulate? And then, of course, so I'm just using the fact that for many of us before, well, actually myself including, before turning to ice crystal, we were asking about droplets. So the question that was being asked is whether turbulence could play an important role in this aggregation process. And effectively, that's what we're doing here. So that was, in fact, a question, an idea that was coming from the meteorological community, and that sort of was passed on to the physics community. But the question is still there, especially for the ice crystals. Okay, so what is the problem I'm going to do? Well, I'm not going to do the full problem, of course. I'm rather going to do some simplified problem. The first simplification, if that thing wants to go, is I'm going to simplify the flow. So, I'm going to sort of imagine that the turbulence higher up is as simple as it can be. Of course, everybody knows that turbulence is complicated, but I will just ignore all sorts of specific things that may happen in clouds and take this sort of paradigmatic flow, homogeneous isotropic turbulence. And then I will also simplify the crystal shape. So that's this little, again, that's something that I'm showing for the third time. And I will just represent that as a thin oblate spheroid, some object with an axis of symmetry, A equal B, and so C here. And with the assumption that A is smaller than any eddy in my flow. I'll come back to that, but so the smallest eddy in the flow is given by the Kolmogorov scale. So I'll just assume that this is smaller than Kolmogorov scale, which is correct. And that this aspect ratio, C over A, is small, of the order of 10 to minus 2. Okay, and well, some people are brave, and you could just try to sort of do the sort of a full simulation using, inverse, fully resolved method, which I know what we're doing. We're rather going to try to sort of obtain some simplified equations to describe the dynamics of the crystal. So, which brings me to the outline of what I will be showing you. So I'll be discussing the equation of motions that we're taking, then I'll be discussing the orientation, and then finally the collision rates and the physical mechanism of collisions. And by the way, if I start going too long, Mr. Chairman, please shut me up. Okay, so equation of motion. So yeah, so the first thing is that one can do is say, well, you know, these particles are small, and then with luck, we can say that there is some zero Reynolds number approximation, which is called the Stokes approximation, which is what people have been doing, you know, yours truly included, to sort of describe the motion of droplets, and with luck, that would work. Well, so in plain English, so there is, we just imagine that our little crystals have a velocity v, and they are living in a fluid with a velocity u, and we can construct the particle Reynolds number as such. So delta u times a is the size over mu. And if we assume that this Reynolds number is small, well, again, with log, we have a good description, and we even have equations. So that's effectively, we didn't invent that. It was just, first of all, it's been sort of very nicely written in sort of the standard books, and it was actually used before by some other groups who were asking similar questions. So we basically borrowed from them. So what you do is you write dV/dt. So there is a term which is gravity, and there is a force which is due to hydrodynamics. And so that one you write as effectively as a generalization of Stokes drag. Well, the generalization comes from the fact that for a sphere that's isotropic, if the object is non-isotropic, then of course you have to take this anisotropy into account by this tensor, the resistance tensor. And well, okay, so we sort of do it in the eigenframe of the object, and then you have to rotate properly, which is done by this R, which disappeared. Yeah, okay. So that's what it is. That's good. And then you have also some torque. Well, the torque. I sort of mumbled that we were going to do things in the frame of the particles. So if we do that, that's a non-Galilean frame, and then you have to sort of correct by having this second term here, which is just the non-Galilean effect. That's what you do when you're probably doing some mechanics early course when you do the Euler talk. That's just that. And there is this sort of a hard part, which is the Stokes torque. So that was conveniently calculated by Jeffrey a long time ago. And I'm sort of giving here one of the expression, never mind the details. So what you see is that it involves the vorticity of the fluid, and it involves the rate of strain. And that's omega is the rotation rate, of the angular velocity of the object. So you have this. And so one of the obvious remarks is that this T is sensitive to the velocity gradient, not to the velocity itself. So that actually is telling you that in my case, where I was, the first transparency where I was showing the light pillars, where there was effectively no velocity or effectively no gradient, when then there was no reason to have any particular orientation of any sort. And in fact, in this case, the thing, any orientation using the equation I'm showing will be possible. And so therefore, it's kind of a hint as to why, asking a question as to why do we see any orientation at all in any circumstance. And okay, so maybe I'll just skip this one for the lack of time. Okay, but so the observation is that the zero Reynolds number limit is actually very deceiving. And of course, we learned it the hard way, and we had worked on this and trying to sort of make sure that it had a life on its own, but no. So in other words, free inertia is always playing an essential role in the dynamics of these ice crystals. So to see that, so that I'm actually so repeating an argument that was made already, but maybe teaching is the art of repeating, right? So if you sort of, so what we do here, or what we use is the fact that if you can do zero Reynolds number approximation, which is Stokes, but you can also correct and sort of in a perturbation in the particle Reynolds number. So that here was the object I was showing, and that's the correction to Reynolds due to particle Reynolds number, and the expression here comes from the group of our colleague here, Professor Subramanian, and it has a force like it has an expression like so. Okay, and that so there is also the notion that you have to be careful because there are possibly also other corrections. Okay, so what the importance of that one? So so if you look at what it is, so now I will so I was sort of be a bit unclear about this v minus u. So now I will just say that the effect of v minus u, that's mostly the setting which is doing it. So there is some downward velocity, which I will call ws, the setting velocity. And if you look at what the torque is, so that's what it is. So this phi here are denoted by this difference, this angle between g and n, and that's this guy here. So with this, you can do some sort of very elementary dynamical systems game. And what you realize is that for example, for a oblate object, there are two two equilibrium position of setting, one with the broad side down, or one with the broad side, the narrow side down. And the sort of simple thing to notice is that with TI effectively favors that configuration, which is consistent with what we had before, namely that, well, in this sort of second transparency of mine, where the thing effectively settled with its orientation horizontally, which was the sort of provoking the maximum reflection. Yeah, so that's effectively, that's a good sign to explain the light pillars that I was showing. Okay, so now the question is, can you neglect one or the other? Because you think, well, TST in principle has Reynolds number, the other one doesn't have Reynolds number. So in principle, with luck, that one should or could be all in some regime of parameter small. And then, so let's just estimate this. So what can that be? So there is be necessarily, like I said, there is some Reynolds particle Reynolds number because that's a small parameter we had at the beginning. So that's would sort of say that that one can potentially make that one small compared to that one. But the catch here is that if you look at what you have, so I told you that that one is not dependent on velocity, but on the gradient, whereas that one is depending on the velocity. So effectively, when you sort of do this estimate, you find not only Reynolds, but also this ratio here, which is a dimensionless ratio of two velocities, one from the setting and the one for the velocity gradient. And when you put the two together, you have this estimate, ws squared over mu delta u. So okay, so and then so then you have to sort of distinguish about what it's going to do depending on the fluid Reynolds number, like so. So for small Reynolds number, well, you effectively just say that the u is u0 over L, where L is a large scale, and that ratio here becomes ws over u0 square over times the Reynolds f. So so then everything's possible. So the things that will create some possible breaking of symmetry with respect to some isotropic distribution is this ratio ws over u0. So that has to be large to see some orientation of sorts. But and then there is this one which if it's small, well then everything is possible. So you could have a symmetry breaking with this one or that one winning depending on this product here. But for turbulence, which is what we're interested in, that's a completely different story. So then that guy here, the new du, that's the velocity gradient of the turbulent fluctuation, and its estimate is a u0 over L times Reynolds to the 1/2. That's some standard turbulent estimate. And then this ratio here would be that. So it means that to have, if the moment you have a symmetry breaking, i.e. Ws over u0 large, well, then that's finished, because that one is large, that one is large, so that one is necessarily large. So to have any symmetry breaking, you have to have Ti large compared to T Stokes. And that, of course, that's this alignment effect that will prevail, not the other one. So that's what took us a long time to understand, and of course, we didn't want to understand, or we didn't want to see, but that's what the equations tell us. Okay, so so that with that, we sort of properly equipped to describe the orientation of small crystal in the turbulent flow. I sort of skimmed, I sort of went very quickly through a slide on which I ignored, because if you just keep the Stokes thing, well, then the prediction is incorrect. Okay, so I don't know whether okay, so maybe I'll just skip that. You can, I'll just sort of say that with this, you can write everything. So you can have a problem where we have a complete set of equation with T Stokes, Ti, and the equation of motion, and the sort of try to repeat to yourself what's going to happen for turbulence. So among all the parameters that are important in this problem are the things that, so some of them we sort of keep fixed, like this sort of beta, or this A over eta, or this rho P over rho F. So two parameters that sort of can vary from one configuration to another, or one crystal to another, are the sort of most sensitive are the sort of the Stokes number, which is the ratio of the particle response time to Kolmogorov time, and that one, the settling number, which is a ratio, if you wish, between the settling velocity and the Kolmogorov velocity, eta k over tau k. So that's just as these sort of two parameters that are important. So if you do the problem in its full glory, so you can effectively calculate the orientation by sort of determining the amount of fluctuation you have around the sort of so what I was calling phi, this difference, this angle between vertical and n, and you can sort of estimate the fluctuation of this as a function of these two parameters. So that's effectively what it is, what the result is. So that's the sort of the details are contained in this paper by Kristian, Gustafsson, and us, well, the whole crew I was showing at the beginning. And so what do you have? So this sort of a dark blue corresponds to cases where the angle is 10 to minus 4. So with a very, very, very little fluctuation. So that corresponds to very strong alignment. And as you go in this direction, what you have are something which is becoming much larger. So then the orientation is lost. And these dashed lines here are, in technical terms, the different asymptotic regimes that we are studying. The sort of most studied regime is this one, the overdamped regime, which appears, for example, I think in Trammell's thesis and in other, in other papers. Anyway, so now okay, so that's again my little result. So I guess fine. So that's sort of a crazy numbers. What is T? What is V? Well, okay. So we are having in mind ice crystals. So ice crystal, and what we have effectively the turbulence intensity up there, which people can measure or estimate. And we have also some geometric characterization of the crystals. And so in blue here, I represent on this very plot the intensity of the energy dissipation from very low to much higher. And here in red, I sort of show the isolines where A, again, the sort of a large scale of the crystal times square root of B, which B being the aspect ratio, are constant. So effectively, that allows you to sort of discuss in a pretty clear way what's going on and where do you expect or not expect strong alignment. And to cut a long story short, what we find is that effectively the alignment effectively corresponds to very low turbulence intensity, which are typical of cirrus clouds, which in fact corresponds to where the things are effectively found, where the very oriented objects are actually found. Well, the sort of what this little model says is that if you sort of go into this regime, sort of with some not even very large turbulence, but some amount of turbulence, well, immediately you are in this regime where the orientation is being destroyed by turbulence. Okay, so so that was solving this model. So in addition, what we've done are doing simulations. Okay, so that the simulation are plain vanilla, nothing fancy, just spectral things at resolution, which are large but not too large, and with some dissipation, which range from 1 centimeter square per second cube to 250, and with different Reynolds numbers. So again, which are not even very large. We basically have run over many TL to conclude about anything. Okay, so here are the parameters that we've been using: A equal B equal 150 microns, and this beta of that order. And again, so the two parameters, which we will be paying close attention to, are Stokes and this settling number. Okay, so one of the consequences of this thing, of course, is that you are expecting that if objects are oriented preferentially with a broadside down, they will be slower than if they are oriented like so. And that's what this little picture is showing. So I'm conditioning the settling velocity on NZ. So when NZ equal 1, it means that you have an object which is very aligned like this. If NZ equals 0, it is aligned like so. And so you see that when NZ small, the settling velocity is faster, just because the resistance is low, and on the contrary here. So by this, I want to show you that there is an important effect about the difference in orientation, and that induces differences in a difference in settling velocity, which will be useful later. Okay, so now collision rate. Okay, so let's try to sort of see where it gets us. Okay, so there is this sort of a general situation where in the general, if you have some solution of particles with a density NC, i.e. capital NC particle per volume, and whatever brings the particles together, so you have a number of collisions that will grow with time. The longer you have, the more collision you'll have. The bigger the volume at a given density, the more collision you'll see. And there is some dimensional number, which is K, which is the collisional kernel. Its dimension are L cube over T. Okay, so what it actually is, it's a flux, right? So what K is effectively measuring the incoming flux of particles towards a given particles. So, and that's how you can effectively interpret everything I was saying. Okay, and then from now on, of course, we sort of just count slavishly the number of collisions that we have in our simulation, and we present the results in terms of this KC, which is proper quantity. And gosh, okay. So okay, so the level of sophistication here is pretty limited. We're not doing any of the things that Bernard was doing. We're not even doing aggregation. So what we do is what's called ghost collision. So we have a suspension, and these particles effectively ignore each other, so they're doing their thing. And then whenever we just analyze afterwards the database and sort of ask ourselves, when do two particles come into contact? And that's how we determine this geometric collision rate. Lots of shortcomings, no doubt. For now, that's the best we have. Okay, so but even that turns out to be non-completely trivial, right? So if you have two little droplets, two little spheres, it's kind of easy to see when they'll be touching each other. Right? Just monitor the distance between the two guys. And that's, well, whenever the distance gets less than the sum of the radii, they have to get into contact. Chris, how would you do it when you have two ellipsoids? It's a little bit of a mess. But thanks God, we have the video game industry. That's the second time in the few years that I realized that there is a fun math going on from this part of the world. They come up with some very interesting solution that tells us how to do it. So what you do is you represent the surface of your ellipsoid like so. So you introduce this quadratic vector xyz1. So then you can write the equation for the ellipsoid as x dot equals 0, and for the other ellipsoid as x b x dagger equals 0. And then what you have to do is sort of ask yourself about that particular polynomial, which is a 4x4 polynomial. The determinant 4x4 matrix. Therefore, it's a fourth order polynomial. And depending on the nature of the eigenvalues, you sort of detect, you sort of know whether the solutions, whether the two objects are far apart, in contact already, or just touch. So effectively, these are necessarily two positive eigenvalues and two negative one. And so depending on whether you have two real negative eigenvalues, the two guys are separated, two eigenvalues with real parts, complex eigenvalues with real parts, they are overlapping, and the contact is just one of this tangency here of the polynomial. So that's something that you have to implement. It's a bit of a mess, but that's what we do. Okay, so with that, we have this collision kernel, which I'm showing here. So what is it? So here I'm beginning by showing this as a function of beta. Beta, I remind you, for different values of beta, I remind you of the aspect ratio of the object. So this ratio between this small compared to the large density, large dimension of the object. And okay, so here, well, the sort of vaguely amusing comment here is that I sort of drew this epsilon to 1/2 line, which is the dependence predicted by Sankar and Turner, as I was mentioned this morning by Bernard, and I guess by Michael the other way. Okay, but otherwise there's some sort of a non-trivial dependence here because the blue is on top at low and the red, so there's some sort of crossing obviously happening here. Sort of to show it in a different manner. So here I'm sort of fixing epsilon and varying beta, and you see that one increases as a function of beta, the other one decreases. Okay, so that's effectively not what you would have called a simple solution. And well, so the results are the results. So why is it that we don't have a nice solution when we vary one parameter and then sort of things sort of fall into some sort of a growing or decreasing line? Well, so that has to do with the fact that there are more than one mechanism that sort of brings particles together. So, in fact, it's not, I sort of mentioned, well, okay, I mentioned two of them already, and the third one comes also comes, can be explained. So the first one, that mechanism that can bring things together, is this sort of turbulent motion in itself. So that was the work of Southman and Turner 66 years ago. I was not even born. And then effectively it's notion that some trajectory of fluid can somehow come together, and if they carry their little particles, that sort of can generate some collision event. So that's the first mechanism. The second mechanism I was alluding to is the fact that, remember, so there are some particles which are under some circumstances pretty aligned, but some may be less aligned. And as they are less aligned, they can actually settle faster. And effectively, so that's what this thing is representing, where effectively, so there is one guy which sort of settles slowly because it's sort of well aligned, and another guy up there which settles faster, and they can effectively collide in this manner. So that's the differential settling mechanism. And the third one is something that was realized as we were studying droplets, which is called particle inertia. So that's the old notion that if you have the fluid is trying to sort of make you turn very, very fast, well, then your particles, due to its own inertia, will not want to do that. And then it will not effectively, the particles will not follow the fluid and instead do something else. So that do something else may actually, so here there is this sort of a suggestion that these two particles are trying to bring, to sort of avoid each other. But if the particles can just follow these eddies, they will just sort of bring the sort of two particles will just collide because, and with a pretty big velocity, because they're just not following the fluid anymore. So that's the three mechanisms that we have. Now, how do we sort of study this? So, okay, so I guess the notion is that it is a velocity difference, which you would expect by sort of a turbulence. The velocity difference will be typically of the order of the difference between two particles times the velocity gradient, which is 1 over tau eta. That's this delta V turbulent equal A over tau eta, which I want to focus on. And this is, by the way, how you were having this epsilon to 1/2. So if you put these numbers together, that's why epsilon half was coming naturally. So now the question is, what is the relative velocity when two particles collide? I mean, is it really fair to say that it's A over tau eta, or is it something else? And the something else, we hope, will pick up the other mechanisms that we're discussing. So let me sort of look at the sort of the simpler one, which is the one at a very low turbulence intensity. Okay, and I will just sort of construct this object, which is sort of the relative difference, delta V times R. And then the notion that if it's due to turbulence in the usual way, that delta V would be typically the distance between the two particles times the number of time, at least as an order of magnitude. Okay, so that what we do is effectively we sort of look at the PDF of these objects. So let me comment. So let's focus first on the left picture. And so that thing delta VR has been normalized by A over tau k. So so it's delta V times tau k over A. So what you see is that for the core of the distribution, they are pretty much on top of each other, which is sort of an indication that effectively, so these particles here are effectively coming together by a velocity difference, which can be interpreted as due to some good old turbulence a la Safran-Turner. Now, of course, for the skinny one, for the one which has the slowest beta, you see that there is all of a sudden this huge part of the PDF. Why is that? Well, why is that? You sort of see it here if you look at this PDF or the cumulative probability distribution function of this orientation. So these two guys here, this sort of the fat one, the cumulative PDF is just concentrating at 1, effectively. So they're all extremely, extremely, extremely stark at 1. So the blue one is a little bit, has a little bit more difference, and that allows you to have the possibility of having this differential settling effect that I was advertising. And if you look at this particular tail of the PDF, that really actually corresponds to the velocity difference induced by the the settling difference between these two guys. So that's what makes us say that, so for these guys, the blue and the, I'm sorry, the black and the red, you are completely turbulence dominated, but, and mostly also for the blue, but for the blue, you start seeing the effect of differential concentration. Okay, so I guess once you have that, I guess if I could, yeah. Right. Okay. Right. So that's just in words. So okay. So maybe for the lack of time, I will not go into that. But effectively, so you can just sort of study one after the other, and convince you that at this sort of intermediate turbulence intensity, it's still mostly differential settling. But when you go to the much higher turbulence intensity, well, then these tails are actually too big. So they cannot come from differential settings. They're rather coming from what some people call sling, what other people call from caustics. But they're coming effectively from the large Stokes effect and the fact that particles don't follow the flow anymore, which is what's being said here. So, and effectively to sort of summarize, we have this little diagram. So we put all our points here. So we have, so in red, points which was a collision mechanism we interpret as coming from Safran-Turner mechanism. The green one, those were the differential settings play a role, and the blue one for which we are reasonably sure that it's the other particle inertia effect. So these guys, we sort of put in some sort of no man's land and sort of a transition regime, where actually several regimes are actually playing a role. Okay, so lesson. So what have we learned? Okay, so there is this very spectacular effect of particles of these heavy crystals, where the inertia due to fluid plays an immense role, and that explains why in sort of a up to sort of weak turbulence effects, the objects are pretty strongly oriented. Yeah, I'm not sure I should read something. Okay, never mind. I'm not going to read. So I know there is also the notion that with this we can sort of understand what are the collision, what is the mechanisms that drive collision. By driving collision, I mean sort of bringing crystals together, possibly leading to aggregation. On some sort of future work, well, you know, there's a number of things that, of course, I've left aside. All everything I did was extremely simplified, including, by the way, this treatment of crystals. So I took from the very beginning the perspectives that I would be considering only some particularly simple form, simple shapes. That, of course, is not the full story. There are many more things here. And I guess one of the perspectives that is perhaps most interesting would be to incorporate the knowledge gain in these kind of things into some realistic modeling strategies. Everybody understands, of course, that if you want to have a code that will do the climate and things like that, you're not going to do what I'm doing. So you better get some sort of good parameterization. And some, well, there is some people who seem to be interested by that sort of aspects and incorporating this kind of knowledge to their bigger code. And with this, I'll thank you for your attention. Dump on you a bunch of references. Some I didn't talk about in particular. So these two guys, Tiang and Cabrera. So that one was trying to sort of justify the model we're doing numerically, and that one was trying to justify the model we're doing experimentally. So some of my colleagues are dropping little rods and trying to measure the torque as it goes down. And the rest are some, the rest are sort of mostly covered. So with this, I'll thank you for your patience and ready to take questions as they come.
All right, thanks a lot for this wonderful talk, Alain. We are ready for questions, so feel free to unmute yourself and ask. You can also raise your hand in the chat. I think there's a question in the chat. No. Yes, Michael. Okay.
Hey, Alain. Many thanks for this beautiful talk. I think I learned a lot of things.
Thank you. It's a biggest compliment.
So for the collision of these ellipsoids, you mentioned this quadratic equation, right? So I didn't quite get that. Do you always need to solve this quadratic equation, or are there like roots available in certain cases? I mean,
okay, of course, if the center of mass, okay, so right, okay. So, we partition the domain, and when there's no chance that we have a lock, we sort of you sort of subdivide your domain into smaller domain, and then you only lock in the smaller domains where you have a chance. If they are just at 100 times the distance between the things, there's just no point in doing that. That's stupid. So of course, we're doing these kind of tricks. Yes.
Yeah. Great. Thanks.
Yeah, sure. No, you're right.
Any more questions? Please go ahead. I had a small question as well. So, I mean, for instance, I mean, a lot of these ice crystals also have a lot of irregular shapes, let's say. So would that, I mean, it's hard to, of course, simulate all of that, but would that increase encounter rates between particles, or is there something one can speculate on that?
Yeah, I mean, I didn't. Okay, so when I showed you this picture of a cumulus cloud, I mean, I sort of told you, I told you I didn't tell you that the picture I was showing was awfully simplified, awfully. So even these things are actually breaking, and so sort of all sorts of things can happen. So so when I was showing also here, so that's so the things indeed. Well, okay, so they are not. You have the as they call it, dendrite shapes. They can also play a role. What I know concerns is that the rest are at that stage. I know I can try to speculate, but I will not pretend that I know the answer. So, like I said, it's a very beginning. No, it's a preliminary thing.
Right. I mean, it's already hard enough to simulate all these things. So I fully understand. I
mean, you're right. No, but of course, when I was sort of bragging and saying that we want to be useful to these people, we'll have to do it. Sorry.
Right.
We'll have to invent something. Which we haven't done yet. But
right.
It's a great question, of course.
Yeah. I think there's a question by Greg. Please go ahead.
Good, thank you, Alain. This is beautiful stuff. Indeed, these are extremely complicated problems, and the question of identifying which complexities to take in first, as we try to take them on, is a huge one. I have one other complexity, actually following closely on that question that was just asked. We all, in our experiments too, we want to work on the symmetric particles, but it's very easy when these things grow for the center of mass to be offset from the center of drag of these particles. Have you considered that case and what effect it has on alignment?
I could joke and saying that the referees have considered it for us. So, okay. We had to wiggle ourselves out. and sort of no, but of course, you're completely right. We're completely right.
It wasn't me, but it may be some collaborators.
No, absolutely. No, I don't accuse you because no, it was a general
cool stuff on this front, where
sorry?
when you get that center of mass offset, then suddenly, you can get opposite alignments that are the stable ones, right?
Of course, yeah, sure, yeah. You have another contribution to the torque, and that can do all sorts of nasty things. Yes, I agree. No, we are considering the sort of this nice little picture of this sort of very symmetric, very clean crystals is what we had in mind. Yes, good point.
And then what the cloud case is, like how symmetric are the cloud particles? I think we don't know, right?
That we don't, but we do. So there's some people who have spent their careers measuring these things. So especially our colleagues in Japan have looked at it in excruciating detail, and there are sort of classification. And so that one is actually some simplified version. But I can sort of dump you some papers which have pages and pages and pages of these guys, depending on blah 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 blah. So that's yes, there is in fact there is a zoo. Clearly there is a zoo. And again, so as you say, we reduce the complexity to something that was tractable. Maybe of course, at the detriment of But okay, so anyway, so at least we are no worse than sort of cloud modelers I sort of discovered last week. They didn't laugh at me because of course there's room to laugh at what we're doing because it's so simplified. But no, they don't laugh. But we should improve ourselves. There's no question.
Any more questions?
Maybe I can say yet.
Yeah.
I fully agree, Alain. And I want to just emphasize that I don't think we have to apologize so much for making it simple. The real world is so complicated that we can't comprehend it unless we find some simple corners where we can say something useful.
Exactly. The question is whether it's useful. I mean, and that's you can always make the wrong guess. So, and we that's what I was beginning. The beginning of the story was just this Stokes-Torque was the case in point. That's sometimes take the wrong equation, you get the wrong answer. But we have to. I mean, it's not finished. I mean, by no any stretch of imagination, we are not finished.
I don't see any other hands up for questions.
It's been a long day.
Yeah.
Well, thanks.
Yeah, I can
thanks
imagine.
Thanks for putting up with me at the end of the day, especially for our colleagues in Asia. That's a boy. Or
not at all. It was a wonderful talk. So if there are no more questions, then I'd like to thank you again, Professor Pumir, for the talk. And I think we can then close the session, I guess. So, Samriddhi, is that fine?
Thank you, Alain.
Yeah.
Thanks.